Well, anyway, it's a pleasure to introduce tonight's speaker, Colin Williams, who's the director of the USGS newly formed Geology, Minerals, Energy, and Geophysics Science Center in the western region of the U.S. He's based in Menlo Park, and until recently he was a supervisory research geophysicist with the Earthquake Science Center in Menlo Park. He also served as chief of the Geothermal Resource Program Investigation Project, with responsibility for assessing the geothermal energy resources of the U.S. and conducting research on improved methods for characterizing and evaluating geothermal resources. His primary research interest is in measuring and modeling the flow of heat and fluids through the Earth's crust, and using those measurements to understand hydrothermal processes, earthquakes, and groundwater flow. He is the USGS representative on the Federal Interagency Geothermal Working Group and is a member of the USGS Energy Resources Program Council, the Science Advisory Board for the Department of Energy, and their National Geothermal Data System, which is the expert panel of the Environmental Protection Agency's Technical Advisory Committee overseeing the City of Los Angeles digested sludge, biosolids, and brine injection project. He joined the USGS in 1989 after getting his bachelor's degree at Harvey Mudd College, his master's degree at UC Berkeley, and his PhD at Columbia. I presume that's really Lamont?
Yes.
Okay, really Lamont. He's co-authored more than 100 technical papers and abstracts and has received the Department of Interior's Meritorious Service Award. Tonight, his talk is The Future of Geothermal Energy, and please welcome Colin Williams.
Thank you. I'm trying to get off that sludge panel, by the way. You're mostly concerned if they injected a lot of sludge underground in Los Angeles if they generate earthquakes. Fortunately, not yet. Now, this is the advancer. Okay. Does this also have the pointer, or is that?
Excuse me?
The pointer. Is this the pointer?
Yeah, that's the pointer. It has a little. It's pretty.
Thank you.
I have to get you better.
It'll work. Okay, great. And thanks so much for inviting me to come and speak at this this meeting. I am pleased in particular to see so many people from the Arizona Geological Survey there. I worried there was a little bit of tension when I was talking with Bob when he first invited me to come. I inadvertently said, "Oh, the AZGS," and he said, "No, not the AZGS, the AGS." And thought maybe that there were some issues between the two organizations, but glad to see that's not the case. I've got a lot of slides, so I'll try to go through this talk pretty quickly. I touch on a lot of different topics, and what I'm hoping is that I won't be too incoherent, but I'll get to the end in time that if you have some questions, we can revisit some of these things. Also, since we're in sort of the minerals part of the world here, I should note that the geothermal effort at the USGS actually got started in the 1960s by Don White, who was initially interested in hydrothermal ore deposits and figured if you want to understand hydrothermal ore deposits, you should go out and look at active hydrothermal systems. That geothermal program, one of the very first things they did when they started growing in the 1970s after the energy crisis was send out geologists to look, or volcanologists actually, to look at a lot of active volcanoes in the US because they figured that would be where some of the active geothermal systems were. And then after in the period of time around Mount St. Helens, when we started the volcano hazards program, it was those geothermally hired volcanologists that started the volcano hazards program. So the minerals part of the USGS is indirectly responsible for both our geothermal and our volcano hazards efforts. I guess I probably need to point that way. Yeah, so just very briefly, I'm going to start off the talk by talking about the overall energy picture in the U.S. in terms of electric power and this really sounds there we go. And need for electricity in the future. cover some aspects of geothermal energy, a little bit on our USGS resource assessment studies, touch on some issues regarding geothermal and sedimentary basins, which we're really just at the beginning of looking at, and go in a little more detail on some of the areas of research and challenges for the future. In the big picture, the United States needs energy supplies, of course, that are secure, uninterrupted, sustainable, economically and environmentally viable. In the US right now, we have a electric power generation capacity of approximately 1 million megawatts. Now, not all of that is online at all times. Some of it's in industrial processes, some of it's is in plants that are only used during part of the year. But the expectation is that over the next 20 years, with our use and interest in growing population, more electric applications for everything from cars to your iPhone and all, we're going to need about 30% more, about 300,000 megawatts over the next 20 years. And so a big question that everybody's talking about in Washington, at least before they were talking about rare earth minerals, is where is all this power going to come from, and how can we develop greater sources of electric power in the U.S. while retaining some sort of limitation on the environmental consequences. And so in the context of geothermal, the big question is, can we make a significant impact in this 300,000, let alone the million that's already online in the US? Now this is from about 2009, I believe, from the Department of Energy. And this shows the snapshot of the US electric power generation mix. At that time, and it hasn't changed a lot. We're getting a little more from natural gas. About almost 50% of our electric power came from coal-fired power plants, about 19% from nuclear, 20% from natural gas, 7% from hydro, and then a lot of other small sources. And all the renewables, this number's gone up a little bit in the last few years with more wind and a little bit of solar coming in, are about 2.4%. Geothermal represents 0.6% of the total, or about a quarter of that 2.4%. So at the present time, although I was maybe a little liberal with the size of this pie slice, you can actually make a visible pie slice on the chart, but it's not very large. Moving forward, and again, this is before the DOE really started to digest the recent boom in shale gas production. This is what the Department of Energy, the Energy Information Administration, or EIA, projected would happen with sources of electricity in the U.S. So they drew a line, and this study was at 2006. All the curves to the left of that line are historical sources of electricity. This is coal, this blue line is nuclear, this purple line is natural gas, renewables is the green, other liquids is this lower purple. And then they projected forward, and as of 2006, they were projecting that progressively more and more of our electric power would come from coal, which of course raises issues regarding CO2 sequestration, clean coal, etc. Probably right now, if the EIA did this curve, they would project natural gas to rise rather than going down because of the boom in shale gas. But how long that's sustainable is open to question. And as you can see, they projected renewables continuing to grow at a fairly rapid rate, but still being relatively modest compared to the other sources of electric power. Another factor that's pushing the demand for renewable energy are these renewable portfolio standards. There's been a lot of debate at the national level about having a national renewable portfolio standard requirement for a certain percentage of electricity to come from renewable sources. But it's been broadly adopted at the state levels, and you don't need or even probably want to look at the fine print as to what each state requires, but generally they are targeting, in some cases these are hard targets or hard numbers, in some cases they're just goals, but they're targeting significant percentages, 15%, 20%, 25%, 10% of electricity coming from renewable sources in various time periods. And I know in California, this original 20% by 2010 has since been superseded by, I think it's 33% by 2017. Another advantage that happens to be true for geothermal is if you are worried about greenhouse gases or CO2 in particular, on average geothermal is a relatively low carbon energy source. So that if you compare the million metric tons of CO2 emitted, this is in quads, which are BTU numbers, but it's basically how much CO2 you get out for a given amount of energy. Of course, coal gives you the most, and crude oil not far behind that. Natural gas about half as much as coal. And then geothermal, again, I emphasize on average, way down here at the bottom. There are some CO2 emissions associated with geothermal. It varies from setting, and I'll talk about that a little bit when I get into the types of geothermal. But it's certainly very, very small compared to fossil energy sources. And of course, there's just the general quality of life. Iceland used to import coal so that they could have heat and also electricity. This is an image, I think this is from the late 1940s. Because of the atmospheric conditions, they used to get these terrible smoke layers hanging over the city of Reykjavik. Now, Iceland, of course, sitting on a mid-ocean ridge, has tremendous sources of geothermal, and they basically use geothermal now for all their space heating and most of their electric power, well, much of their electric power. A lot also comes from hydropower. And this is, of course, the way Reykjavik looks today, because they, in essence, have very low emissions associated with any of their sources of heating or electricity. Now, I'm going to talk a little bit about some different aspects of geothermal energy. Of course, it's concentrated in places where there's a lot of anomalous heat in the Earth's crust at the boundaries of the tectonic plates. This figure map just kind of illustrates the general distribution of tectonic plates around the world, and of course the plate boundaries and all the major volcanic centers associated with those plate boundaries. And if you wanted to know where geothermal resources are, they're basically where the heat is and where the tectonic activity is. So the western US, the Aleutians, southern Alaska, Japan, Italy has some of the largest geothermal fields in the world, Iceland, various parts of South and Central America. Indonesia and the Philippines are developing geothermal at a tremendous rate. The United States has been for many decades and still is the largest single producer of electricity by geothermal means, but Indonesia is coming up fast, and Philippines is not far behind. Of course, in some of these areas, geothermal manifestations are quite spectacular. There's one of the geysers at Yellowstone, I actually forget which one, and it's relatively easy to find, perhaps a little bit hard to handle, but in certain locations, the hot water and the steam associated with water, if it's hot enough, is relatively abundant. The challenge comes in the application of finding large geothermal reservoirs for electric power or other uses, and in categorizing the resource. So at the USGS, traditionally, we've looked at it in this context. Basically, broadly considered conventional and unconventional geothermal. Conventional geothermal being related to hydrothermal systems, whether they're relatively low temperature and suitable only for direct use. Typically, those are systems that are less than about 90 degrees C or about a little lower than 200 degrees Fahrenheit. Or whether they're used for electric power generation, which of course are also suitable for direct use applications, such as space heating and greenhouses, snow melting, etc. And those traditionally have been divided into moderate temperature systems of between 90 and 150 C, and high temperature systems of greater than 150 C. There are also categories of geothermal resources that we refer to roughly as unconventional. Enhanced geothermal systems, which I'll talk about in some detail, and of course some of these deep sedimentary basin resources that I'll touch on, such as geopressure geothermal and the co-production of geothermal with oil and gas production. And these three that I've highlighted in green were the ones that were the focus of our most recent resource assessment effort. Now, a key factor in geothermal, just like any subsurface liquid resource, is that you need to find the fluid. You need to find that permeability, a place where you can drill underground and bring that fluid into a well and bring it to a surface. And of course, since we're talking about hot water or steam, you need the high temperatures. And those places where you get the co-location of high temperatures and hot fluid moving rapidly underground tend to be places where there's a high background geothermal gradient, like in the Great Basin, or volcanic areas such as the Imperial Valley or the Geysers Clear Lake geothermal area in Northern California. And also where you have pathways for the water to flow. In this schematic, this could be kind of an idealized basin and range geothermal system where you've got hot water flowing up the active fault zone that forms one of the boundaries of the basin. You typically have some sort of cap rock, something that isolates the hotter geothermal fluids from the cooler groundwater that might be flowing in the shallow subsurface. There may or may not be a thermal manifestation at the surface. There are often, if there's not an active thermal manifestation, there may be fossil records of past hydrothermal fluid mineralization. And of course the objective is to drill down, find this hot water, tap into it, run it through your power plant to generate electricity, and then re-inject the cooled water back underground so you can maintain pressure in your geothermal reservoir. Different ways of generating electricity from geothermal fluids. The most common way in terms of the number of plants that use this technology is the hot water flash system, where the water is hot enough once you bring it from depth to the surface, allow the pressure to drop. It's hot enough that it will naturally flash to steam, so you end up with liquid and steam or vapor portions from the water you produce. Typically you run it through a separator like this to isolate those, because a lot of any solids that come up with the geothermal fluids will remain with the liquid portion. You run the steam through your generator and produce electricity, then you condense it back into its liquid phase and pump both back into the subsurface formation. The largest geothermal field in the world, the Geysers geothermal field north of San Francisco, also the Larderello field in Italy, are what are known as vapor-dominated or dry steam fields. The water exists as steam underground, and there, consequently, the situation is relatively simple. You drill your well, you allow the steam to flow in, and you just run it right through your turbine and inject the returns back underground. Finally, for the lower temperature electric power applications, those moderate temperature systems I talked about, you have to use a binary power plant, because the water isn't necessarily hot enough to produce a significant amount of steam, or it may even be, although it's warm, not hot enough to, by the time you bring it to the surface, to even flash to steam. Typically you just bring the hot water through a heat exchanger, and it exchanges its heat with a fluid of a much lower boiling point. Typically these fluids are things like isopentane or isobutane. They have a much lower temperature at which they turn into a vapor phase, and you cycle the isobutane or isopentane through a turbine, generate electricity that way, and then send it back through the heat exchanger. Meanwhile, the water you've sent through the heat exchanger that's cooled off some gets ejected back underground. The one attractive aspect of binary power plants is that it is a closed loop system. You don't lose any water. Both kinds of flash steam power plants, you lose a certain amount of water from your reservoir out your condenser, your cooling towers, and you have to make up that water somehow, or else you have problems with pressure maintenance in the reservoir. Right now there are more than 2,500 megawatts of electric power generating capacity in the United States associated with geothermal power. Numbers run up to about 3,000, it depends on how you count it. There's about 400 megawatts thermal and direct use applications, typically for things like greenhouses, aquaculture, space heating. Especially space heating is really common. There's more than 1 million geothermal heat pump installations, which essentially use the natural stable temperature of the ground as a heat source and sink for space heating. And we've been working since about 5 years ago on a very progressive project on updating the geothermal resource assessments, which the USGS last did in the mid-70s and early 80s. And of course working with DOE and a number of other institutions on all of these problems. So a little bit about our resource assessment. The work we completed in 2008, the part that we undertook at that point were to tackle identified geothermal resources, those moderate and high temperature systems capable of producing electric power. We looked at undiscovered resources and estimated their possible distribution and extent, and then developed what we call a provisional assessment of enhanced geothermal systems, and which is a relatively new and somewhat unproven technology, at least unproven in the commercial sense, of a way to create geothermal reservoirs where they don't exist, but the rock is already hot. These maps show the distribution, the black dots, which are a little bit hard to see. I'll have to change the color on this map. Distribution of identified moderate and high temperature geothermal systems in the United States, on the Big Island of Hawaii and the Kilauea Puna and the Kilauea Rift Zone, on the Aleutians, associated with many of the volcanoes out there like Akatan and Makushan. There's a belt of geothermal systems in central Alaska heading out on the Seward Peninsula. Then, of course, in the United States, large number associated with the Basin and Range Province, some in the Rockies, Snake River Plain, the Cascades, of course, the volcanic arc there, the Geysers Clear Lake region north of San Francisco, and the Imperial Valley. There are a couple in Arizona, southeastern Arizona, near the border with New Mexico, and a large one that is now part of a national monument at the Valles Caldera in northern New Mexico. And when we look at the potential electric power production from these geothermal systems, we use what we call a Monte Carlo simulation to try to estimate the potential power. I probably shouldn't, I won't go into details here, but basically we develop statistical estimates of possible ranges of reservoir temperatures, reservoir volumes, what kind of thermal energy recovery you can get from the reservoir, some other factors, and run them through in a model that gives us a probabilistic distribution of what a given geothermal resource might look like. In this one, you can't read it, but I can. The mean geothermal power potential of this particular site was estimated to be about 15 megawatts, with a 95% confidence of at least about 4.5, and a 5% confidence of 32. And those are sort of representative numbers where we try to bracket what the uncertainties are in these potential electric power estimates. Because in most of these identified systems, there's very little commercial activity. Of the 240 systems that I identified, only about 20 are actually producing electric power right now. Many others have been studied or explored by industry, but we still know very little about a lot of these systems. And as with many geological resources, a lot of them are small and a few of them are large. It's sort of a log normal distribution where we get this estimate that when we add them all up, there's about 9,000 megawatts of potential from identified systems, so about 3 times what's currently installed. But most of them are relatively small, nearly 150, less than about 10 or 20 megawatts, but a handful up in the hundreds of megawatts, and 2, the geysers and the Salton Sea geothermal system up above 1,000 megawatts in power generating potential. We looked at undiscovered resources, trying to find factors that we could quantify the relationship with the favorability of the formation of hydrothermal systems. This map represents one set of models to identify areas of elevated geothermal potential. And as you can see, there are areas that tend to correlate a great deal with the existing distribution of geothermal resources. And our best estimate is that the mean undiscovered potential is about 30,000 megawatts. So about 3 times as much may be undiscovered in the western US and in Alaska and Hawaii as we know about. Which of course, in the context of the western US and the power demands in the western US, means that geothermal is a significant regional resource. I think the electric power capacity in California is about 54,000 megawatts. Smaller numbers on the order of about 10,000 or so in many of the other western states. So if you increase geothermal from, say, 3,000 megawatts to 10,000 megawatts, you're actually making a significant dent in the power demands of the western US. But at a national scale, it's not that big a deal. So that's where the enhanced geothermal systems come in. Many of these places that I highlighted on the map that are shown as high favorabilities or many of the areas surrounding active magmatic areas or regions of hydrothermal systems have a lot of relatively impermeable hot rock surrounding them. So the idea has always been, if you can go in and drill in and create fractures of your own and create a geothermal reservoir of your own and exchange water through that reservoir, you've got a heat exchanger, you've got the ability to create your enhanced geothermal system. You have much more flexibility as to where you could put it. One of the problems with the existing geothermal resources is that many of them are at remote sites, and it costs a lot of money to run power lines. So if you have a resource that may be 10 megawatts or 20 megawatts, but it's out in the middle of nowhere or out on an Aleutian island, the odds of getting it locked into the power grid or finding some use for the electricity you could generate are very low. There are many more options with where you could put an enhanced geothermal system. There are less concerns about exploration costs. The problem is making the technology work. And just to emphasize my points, there are large regions of the United States where there are high temperatures at depth, drillable depth. We take it at about 6 kilometers, and the thermal energy in these areas is many orders of magnitude greater than the thermal energy in hydrothermal systems. But there are various technical issues as to how to make this work. Typically what they want to do with an enhanced geothermal system is replicate some of the natural processes that create permeability, in particular the processes that create permeability due to fault slip on natural fractures. So on the left you see this is actually from a rock that's exposed near the Coso geothermal field, where you've got a fracture here, you've had slip on this fracture, repeated episodes of opening, water flow, sealing by mineral deposition, then subsequent opening again as it slipped. And the idea is that by pumping water at relatively high pressures into pre-existing fractures, you can cause them to slip and you will generate more permeable pathways. Now this is a different sort of hydraulic stimulation than what you hear about in terms of shale gas, like in the Marcellus or the Bakken formations in the central and eastern part of the U.S. In the petroleum industry, when they do a hydraulic fracture stimulation, they typically pump large amounts of fluid at very fast to create pressures sufficient to overcome the least horizontal principal stress and generate what's known as a tensile fracture. Basically, the two sides of the fracture open up. They don't slip past each other, they just move away from each other. In EGS, what we do, or what we try to do, is to pump in water at a somewhat lower rate and somewhat lower pressure, but enough that the pressure builds up and causes slip on pre-existing natural fractures in what are already fractured but relatively low porosity formations. And the idea then is then these networks of fractures link up, you create your geothermal reservoir, you can drill into it again with a production well and cycle fluid through it. This has been done at a number of places on an experimental basis, the most notable one being the Sulz project in eastern France, which is in the Rhine-Graben, and was a combination German-French project. This cloud, this is a sectional view of the Sulz field running from about 4 kilometers down to 5.5, and a map view showing the density of microearthquakes that were created by this hydroshearing process that created the reservoir that these wells tap into for circulating hot water and generated about 1.5 megawatts of electricity. So looking in the western U.S., this is a map, one way of looking at temperatures at depth. This is a contour of temperatures at 6 kilometers, and basically anything that's orange or red is very favorable for EGS. If you find it economical to drill at those depths and stimulate. MIT and a panel, well, it was a professor at MIT, Jeff Tester is now at Cornell, and a panel that was funded by the Department of Energy, delivered an assessment of anywhere from 1.2 to 12 million megawatts potentially available if you could do EGS down to 10 kilometers across the entire U.S. We focused in 2008 on the western U.S. where the highest temperatures are, and we were already looking at the hydrothermal systems, limited it to 6 kilometers, and still came up with a figure on the order of 500,000 megawatts. Google's been funding some people in recent years, and again, for the entire US, estimated perhaps as much as 3 million megawatts. Now, there are a lot of things that have to happen before this could become a reality, but again, the bottom line is that if EGS can be made to work, you have this flexibility of where you can put it, and you have this tremendous resource that if you can only tap a small fraction of it, it's a big player in electric power. The other advantage of EGS, because as you saw in that previous map, wide distribution of high temperatures at depth around the western US, is it evens out the geographic distribution of geothermal resources. So this pie chart on the left shows the identified geothermal resources, which are dominated by the large systems in the Salton Sea and the geysers in California. Nevada is second, Oregon is third, or actually Alaska is third, and Oregon is fourth, and other states such as Arizona, which you really can't quite see here, that's about 0.29%, don't get very much of the pie. Similarly, we think the undiscovered resources are not as heavily weighted to California, but they're still, they are still strongly weighted to California and Nevada. And although there's more potential in some of these other states, it's not a very large fraction. But when you get to EGS and you're just looking at the thermal resource, because there's high heat flow in places like Arizona and Oregon and New Mexico, their share of the pie is much larger. Here's Oregon, New Mexico, and Arizona. So not only is there a large magnitude of the EGS resource, there's a greater geographic distribution that could be attractive to many states. And just very briefly, I don't want to go on too long here, I want to highlight that there are other geothermal resources, in particular the deeper parts of sedimentary basins. Of course, we have a lot of sedimentary basins all over North America. Most of them involved in oil production. In some cases, the oil comes up with water that's hot enough to be used for geothermal. And at the Rocky Mountain Oil Test Center in Wyoming, better known as Teapot Dome, they're actually generating electricity from hot water that comes up with the oil that they produce there. It's, again, a Department of Energy operation. And there's also geopressure geothermal, primarily along the Gulf Coast of the Gulf of Mexico, where there are high pressure brines at depth, and some idea that if you can maintain high flow rates from these wells that have high pressure brines, you can have a successful commercial operation. Oops, wrong way. Finally, I'd just like to focus a little bit on what some of the challenges are with respect to geothermal, some of the problems we need to solve. Now, I'll touch on a couple. There are a whole lot of issues to address in the future. One is the availability of exploration technology and the extent of deep geothermal resources. Another I'm going to touch on is an induced seismicity problem related to enhanced geothermal resources, and a little bit on the availability and quality of data. There are a wide variety of techniques used for geothermal exploration, many of them taken from the mining industry or the mineral exploration industry, a few from oil and gas, a few developed specifically for geothermal. The top three are these. Of course, a lot of geologic mapping, shallow subsurface temperature measurements, heat flow measurements to identify thermal anomalies, and then water chemistry, because with the water chemistry you can do what's called geothermometry. You can sometimes be very successful in reconstructing the thermal history of water you collect from a hot spring or well and estimating what its reservoir temperature is at depth. Electromagnetic surveys of various sorts have been successful in a lot of cases, particularly in volcanic terrains, a lot of reliance on potential field and gravity and magnetics. There's growing use of remote sensing, especially this hyperspectral remote sensing that gives you some idea of location of hydrothermal mineral deposits on the surface, which could be used to infer the locations of possibly active upwelling zones. Not a lot of seismic, mostly because geothermal tends to be in places where seismic's hard to collect in high quality. The other factor is that geothermal fluids aren't as profitable as oil, and so the money involved in, say, a large 3D seismic survey just doesn't work in the geothermal context. And so one of the big needs is for better, more cost-effective techniques for finding and characterizing geothermal resources. But this is an example of one success. This is a contour map of inferred resistivity at depth in Glass Mountain, which is in Northern California, also known as Medicine Lake which is volcano, which is centered right around Medicine Lake itself, which is here. And basically, the red areas represent highly conductive zones at depth around the rim of the volcano, and blues represent resistive zones. These conductive zones are associated with clay alteration that forms the cap to the hydrothermal reservoir at Glass Mountain. There are also, although these aren't quite on the same scale, thermal anomalies associated with those same sites. And if you draw a cross section through there, you see the clay alteration, the high conductivity zones associated with the cap rock that seals the hydrothermal reservoir. The higher temperature alteration results in greater resistivity or lower conductivity at depth in the reservoir itself, and the deep drilling confirms the high temperatures related to hot water upflow. Problem, for example, in this case, is that while this data were collected by magnetotelluric techniques, while they're very good at imaging the cap rock, very good at imaging the conductive alteration zone, the MT technique really can't tell you much about the reservoir depth. And there's a lot of heterogeneity in the reservoir at Glass Mountain, so there's been a lot of hit or miss in terms of drilling, in terms of whether they're actually getting into upwelling zones or not, or permeable zones or not, because the geophysics don't allow them to really resolve the structure of the reservoir. And this, I'll skip over this, but this just highlights some of the alteration processes that occur. Similarly, in a case like the Basin Range, where there might be upwelling water at depth, but that's trapped under cap rock, perhaps flowing in rocks at greater depth, you might not have a surface manifestation or even a particularly large shallow thermal anomaly associated with the geothermal system. And in some cases, those geothermal systems, those deeper systems, have only been discovered by serendipitous deep drilling. And one example, so there's a drill rig. One example is in Railroad Valley, which is in somewhat southeastern Nevada, or sort of south central Nevada, I guess I should say, where there happen to be some of the most prolific oil fields in Nevada, which there are not too many, but significant ones in Railroad Valley. This is a map of the valley. The valley runs here between the Grant Range on the east and the Pancake Range on the west. And in particular, this is from a paper published a number of years ago by Jeff Hewlin, who was a colleague of Lee Allison's in Utah. The Grant Canyon and Bacon Flat oil fields in the middle of Railroad Valley are associated with very anomalously high temperatures. In fact, the people drilling those fields originally had to abandon one of the first wells because the oil came up with boiling water and scalded the drillers. And the reason nobody knew about the geothermal system until they were drilling for oil is because the geothermal system is associated with deep circulation of water and masked by shallow, cooler groundwater flow. So the valley fill, this is a cross section through Railroad Valley. Valley fill is about 4,000 or 5,000 feet deep. There's cool groundwater moving through the valley fill, but underneath that in deeper carbonate rocks, there's circulation of hotter fluids that's associated with the accumulation of oils in the carbonates and the formation of reservoirs. So the only way they were able to discover the high temperature geothermal system in Railroad Valley was by imaging the oil using standard oil field exploration techniques, imaging potential reservoirs and drilling into them. And this became really important in the context of the thermal imaging, because when you get deep, you can find a significant thermal anomaly associated with the Railroad Valley geothermal system, but only when you get to depth. And in particular, these are measurements of heat flow we made in deep wells at Railroad Valley. And heat flow is generally reported in these milliwatts per meter square values. Higher is better, of course, if you're looking for geothermal. And in the upper 1 kilometer or so of these wells, the heat flow, due to the shallow groundwater circulation, is either low relative to the average in Nevada, in this case about 50, or just about equal to the average. If you measured heat flow in the upper 1 kilometer in Railroad Valley, you wouldn't see any geothermal anomaly. But you get below the shallow groundwater system into the region above the hydrothermal system, and the heat flow practically doubles. And is clearly anomalous, is clearly associated with high temperatures at depth. Finally, I just want to touch on one significant problem, and that's induced seismicity. Seismicity, microseismicity, which generally refers to earthquakes that are too small to feel on the surface, is a tremendous tool in these enhanced geothermal system projects because the microseismicity, recording it with seismometers on the surface or in shallow boreholes, allows people to see the spatial and temporal progression of the stimulation that they're doing to create the reservoir. The problem is that sometimes these earthquakes get a little too large in magnitude. And there was a similar EGS project like Solz that was conducted in the city of Basel in Switzerland a few years ago. And as they were stimulating the, creating the reservoir and generating this cloud of micro-earthquakes, they had an earthquake above magnitude 3. Now, in California, magnitude 3 isn't that big a deal. But in the middle of a Swiss city that was destroyed by an earthquake in the year 1300 something, it is a big deal. And they shut down the project and they actually put the operator on trial and charged him with various crimes. So there's been a lot of concern with EGS that if you do it in the wrong area, or perhaps most areas, and you start to generate damaging earthquakes, it could be the Achilles heel of that technology. And in particular, just a couple of years ago, DOE was funding Ultrarock Energy to test EGS technology in low permeability rocks below the geysers reservoir. These are some power plants at the geysers in Northern California. But somebody at the New York Times who was actually in Basel at the time of the magnitude 3 earthquake noted that they have earthquakes in the geysers. And this is because there is a lot of injection and production at the geysers. There is some seismicity associated with the geothermal operations. And normally it wouldn't be a big deal, but there are some disturbances to the people of small towns of Cobb and Anderson Springs right near the geysers. And the press picked up this idea that if they started doing EGS at the geysers, maybe the earthquakes would get even larger. Most of these are relatively small. They're about magnitude 2 or 3. Every once in a while they get a 4. And so all of these things hit the news in 2009. New geothermal project raises questions. Deep in bedrock, clean energy and quake fears. Small town fears quakes from geothermal energy project. And basically, it killed the project. DOE got around to permitting the project after the company that was doing the work decided they couldn't wait anymore and getting approval and pulled the plug on the funding. So in essence, it was killed, but that's partly because concerns about earthquakes are in many ways legitimate, and there wasn't a good technical basis for addressing some of these issues. So now it's a very high priority with a lot of the DOE funded projects to deal with this induced seismicity issue and enable predictive modeling so that there can be confidence that maybe you might get a magnitude 3, but it's in a location where a magnitude 3 isn't a problem. Are you going to get a magnitude 4, or what's the probability associated with that? And then finally, just to touch on, since Lee and his friends at the AZGS are here, is the real need to improve the availability and quality of the data. Geothermal is a small industry. There's not a lot of money in it. It's been around for a long time, but the government funding and other funding has gone up and down with the price of oil and other energy sources. And a lot of good quality old data has been hard to find and hard to rescue. And there are newer sources of data and models coming along. We have to be sure to preserve those. For example, there was recently at the USGS a study that produced a 3D subsurface model of the geology at Biawaway, Nevada, which is one of the producing geothermal fields, providing all sorts of detailed information on the subsurface structure. These are the kinds of products that typically show up in a journal as a figure. We want to be able to make sure that these detailed surfaces and their digital representation are available to a wider audience. Similar, as we refine our picture of geothermal areas over time, this is a map of the heat flow in Southern California. Here's the Salton Sea. Here's the California-Mexico border. Some state, Arizona. Arizona's over here. That you can see these general contours. Well, now we've got enough information that we can be much more specific. in terms of our locations and the details of contour and thermal variations in the Imperial Valley. We want to be sure this data gets out into the public and is preserved. And so that's where Lee and his project with DOE at the National Geothermal Data System is very important, because they're doing the hard work of knitting together all these efforts in geothermal and bringing those data in an accessible form. So just to summarize, and I have to read this, so I'll turn away, is basically, if we're going to have increased exploitation of natural hydrothermal resources in the United States, we need cheaper, more innovative, improved exploration techniques. We need better modeling of the data we do collect and successful integration of multiple data sets. If we're going to develop EGS and begin to realize even some tiny fraction of all that large resource that's out there, we need to be able to better develop predictive models for how the reservoirs will perform, what things are like in the subsurface, and we need to mitigate any risk that's associated with induced seismicity. At the USGS, we have a lot of work to do updating assessments to expand them to include sedimentary basin resources, and the path forward to all these depends to a degree on successive efforts like the NGDS. I think that's it, except that I don't do this by myself. There's a lot of people, a lot of institutions that contribute to geothermal, and that's it. It's not even 9 o'clock yet. Wow. Question?
You just made a comment, you said mitigate any risk. At what point does the public need to understand that there is no free lunch and that there's risks associated with every form of energy, including geothermal?
That is a difficult question. We did a
question because most of us back here.
Oh, it was basically, at what point does the public need to understand that there's no free lunch and that there's some downside associated with any source of energy? That was a couple of years ago. We did a briefing back at in Washington to some congressional staffers on induced seismicity, because even though it's relatively new in geothermal, induced seismicity has been around for a long time. They were associated with reservoir impoundment, mining operations, etc. And some of the staffers were practically ranting because they run into this kind of issue all the time. They have carbon CO2 or CO2 sequestration projects that they can't get going because of local opposition. They have other projects that they're trying to support, funding they're trying to give to various agencies in the federal government or local governments to do things, and they run into local opposition. And similarly with geothermal, yeah, to what extent should, if this is a low carbon fuel, it's renewable energy, it's good for the country, how do you balance that against local issues? On the other hand, the people who live in those towns near the geysers, for example, these earthquakes are real and they do feel them all the time. And I think that's really a question for sort of our wider political system, is how to figure out a way through this energy problem by properly balancing all those issues. Yeah.
Along those lines, what about the impact on the aquifer systems, and in many places where geothermal has forced some of the natural hot springs to shut down, or some of the geysers have shut down, and it seems like the future of geothermal could be greatly impacted by some newspaper reporters getting it out and the public outrage.
Yeah.
And just like mining gets shut down, geothermal could just as easily be shut down.
It's one of the reasons why the binary power plant application, the closed loop system, is very important, because if you do go to places like Kozo Hot Springs is not really doing anything anymore. Biawaway, the geysers there are gone. There are, you start sucking the hot water out of the ground at greater depth, it doesn't make it to the surface to feed your hot spring anymore necessarily. And so there are these trade-offs. A lot of these developments took place before people really were concerned about the impact on the surface features. Although there are areas of that are codified in federal law of significant, I forget what they call it now, significant thermal features is what the law says. And so, for example, there's not going to be any geothermal development in Yellowstone. That's off limits. Areas around Yellowstone are off limits. Mount Lassen and the areas around the Lassen National Park are off limits. There's seems to be a nice hydrothermal system under Mount Rainier. I'd love to drill into it, but that's off limits. Valles Caldera is off limits. So a lot of the prime geothermal areas are off limits in part for the same reasons that you highlight. So at least those most precious ones will be preserved. Yeah. Yes, you. Wait.
You know, one way of looking at these things is they're simply oil deposits, and you're trying to extract heat and sell the product. So with all the costs of exploration, development, maintenance, and delivering it to the pump, if you will, is there any place today that you could do this without federal support and actually start mining in the United States? Has it become economically possible, or?
You mean in the context of geothermal? Yeah, a lot of the early, the larger fields, the ones that were developed early, there was a fair amount of federal involvement, but at the same time, these were the big obvious first fields you started with, like the geysers, like the Salton Sea, so that while the federal government, the Department of Energy played a significant role, I think they would have been developed anyway, because they're so obviously economical. Some of these other places, it's pretty dicey. A lot of geothermal companies, well, no geothermal company has the deep pockets of the oil industry, and so they have a hard time floating a large-scale exploration effort without the support of the Department of Energy. Yeah.
It's more of an opinion question. Do you think one potential advantage of geothermal energy as compared to other renewable energy forms might be in its ability to interest, for instance, the oil companies that might be reluctant to go for wind or solar power because geothermal power uses more of the technologies they already employ, like drilling, seismic?
Yeah, that's actually a very insightful observation. I was at a conference last year in Napa, Hedberg conference on enhanced geothermal systems, and there was very strong representation by the oil industry. They don't see it as very profitable in the way that these days with the price of oil that oil is, but they're being pushed or encouraged or choosing on their own to diversify their energy base, and they find geothermal, at least the enhanced geothermal systems potential, attractive for those very reasons, that it's using technology they're familiar with, they're used to developing subsurface resources that only pay off in the long run, don't pay off in the short run. They see EGS as interesting because it's large, and it's the kind of thing they can relate to. They don't like little 10 megawatt power plants. They want to drill 1,000 megawatts. They want to go out there and do something big. So there may be an oil company involved.
You may not be able to answer this, but I'd like to play that backwards. The geysers was originally the domain of Union Oil Company.
Yes.
And they did all the drilling before any of the commercial power companies were interested. And Union Oil had a hell of a time trying to get PG&E and the rest of them to go up there and develop the geothermal resource. So how did Unocal get out of that?
Yeah, well, that actually, there is a tremendous backstory there, and they were involved. Phillips, Shell, Union Oil, Texaco at one point. I'm probably forgetting Sun, all these ones that are now merged and merged again. For some of those same reasons, they saw geothermal as their kind of resource, a subsurface liquid resource they could drill. Some of them dropped out in the early days because they weren't very successful. Others, Unocal, there was a guy at Unocal named Carl Ott. Some of you may have known him. He was high enough in management that he could influence company policy, and he was very enthusiastic about geothermal. So he pushed Unocal into all these places, like the Salton Sea. They did a lot of the early work there, like the geysers overseas in the Philippines and Indonesia. And then at some point the company decided, when geothermal wasn't very profitable and the price of oil was low and the price of natural gas was low, that they wanted to be an oil company and get out of the geothermal business.
So they're out of that entirely now.
Except for the Philippines and Indonesia, because they had some legacy projects there. Chevron's, I forget which one. Chevron is in the Philippines and Indonesia, and Unocal's in the Philippines, I believe. Well, I guess Chevron owns Unocal now, that's right. They're in the Philippines and Indonesia. One was in one and one the other, and then they merged. And those are highly profitable legacy projects that they kept. because of arrangements with the local government. Basically, Indonesia is happy to produce their own geothermal power and sell everybody else their oil. Yeah.
Is there any move afoot to change geothermal leasing procedure, whereby now if you identify a geothermal area that's thrown open for anybody and everybody to, put a bid on it with a heavy capture area?
Yeah, when we were first starting on this renewed assessment work, because I didn't mention the USGS basically got out the geothermal business in the mid-90s, same time all the oil companies were, and then got back into it again with the need to update the assessments and address renewable energy. About the same time, there was a lot of push to change the geothermal leasing rules and to bring back some competitive leasing and get rid of the known geothermal resource areas, etc. And so under the Energy Policy Act of 2005, I think it was, they made a number of changes in the leasing rules, and Congress thought they were doing what the industry wanted. And since then, I've heard a lot of grumbling, especially directed at my colleagues at BLM, about the changes in the geothermal leasing rules, and a lot of comments like what you say about the need to maybe go back to some non-competitive leasing in parts of the country. I don't know the answer, but I think there are certain parts of the industry that would be happy if there were some changes. Yeah.
Hydrocarbon production and some renewable energy production has gone offshore. Is it thinkable that geothermal energy goes offshore?
I think there are some areas in the Gulf Coast, especially in the near offshore in Texas. The state of Texas had looked, the Bureau of Economic Geology has looked at that. Possibly the near offshore, other places in the Gulf of Mexico where you wouldn't have to go very deep, where basically you can feed the wellhead right up to a shallow platform. There's some feasibility of doing geothermal. You get to deep enough water, then you're running into big thermal problems. You can't get that hot water to the surface. And the reservoirs in the deep Gulf, they're relatively cool. All the water and oil that were coming out of the Macondo well when it blew out, which made it, because it was uncontrolled, like the most prolific producer in the offshore Gulf of Mexico, would barely have powered a few megawatts of geothermal electricity because it simply wasn't hot enough.
The California and Nevada fields do not stretch into the Pacific?
Well, I'd actually love to do the Gulf of California, south of the Salton Trough and south of Cerro Prieto, which is in northern Mexico, and one of their biggest geothermal field. All the little spreading centers in the shallow Gulf of California would be awesome targets, but
Well, the
I'm not an
Baja
explorationist.
California has a power plant.
Yeah. Yeah, same structural trend.
Thank you.
You mentioned that oil companies are gonna need a little push to go into the geothermal business again. What type of push would that?
Actually, probably what would work best is a pull, in the sense that one thing I didn't mention about the oil companies being in it in the past was there was this, I forget the name of the public law, but in the geothermal industry they used to call it Standard Offer 4. And there was a law that was in place until the early 90s that guaranteed a certain minimum price for geothermal power had to be purchased by the utilities. So a lot of the projects that were developed in the 70s and 80s had a guaranteed floor on their price that made them much more attractive economically and were part of what interested the oil companies. With the fluctuating energy prices, especially when you're looking at if you develop a geothermal field, it may not pay off for 10 or 20 years. Companies are really looking for economic stability when they're doing that kind of long-term investment. And so, as taxpayers, even though of course I work for the government, but I still pay taxes, we may not be enthusiastic about subsidizing the price of electricity. I think that's the kind of thing that would attract a lot of industries into geothermal if they could be, if they knew there was some foundation to the economics they were dealing with.
I know that your group doesn't get into economics, but the one thing, could you give just a qualitative idea of, first place, the relative costs per unit of energy for, say, hydrocarbons versus nuclear versus geothermal, and then also relatively for capital costs for hydrocarbons, nuclear, and geothermal?
Okay.
Very, just in a very qualitative
Kind
way.
of ballpark figure. Of course, it all depends on what's going on with shale gas and everything, but people I've talked to, like, the city of Palo Alto in California runs its own utility district. And a couple of years ago, they were buying conventional power, whether it was natural gas or some other source, at about 5 cents a kilowatt hour. And for them to get geothermal, they had to be willing to pay about 10 cents a kilowatt hour. So it's in the ballpark, but it could be as much as a factor of 2 more expensive. Again, it depends on the source. In terms of the capital investment, the power plants cost the same. A steam, a turbine power plant is pretty much similar. If you're not using, if you're using natural gas to run or whatever, it's still pretty similar in cost. The wells can cost a few $1 million a piece, so that's an additional cost. The challenge with geothermal, and as I mentioned, the attractiveness of enhanced geothermal systems, is that if you're in Dixie Valley, Nevada, or Biawaway, or Blue Mountain, or Fish Lake Valley, or wherever, you've got to run power lines to those places. Whereas with your natural gas, you just stuff it in the pipeline and run the pipeline probably goes to wherever you'd like to hook up to the power grid. So there's the transmission cost can be the source that makes the real differential between geothermal and a lot of other power sources.
My understanding is that to produce nuclear energy power, it's relatively low per unit of energy, but the initial capital costs are enormous.
Yes, that's true. Thinking of nuclear, absolutely. And then there's all the costs they have to put aside for the unknown disposal of waste in the future and everything, yeah. Any other questions? Okay, well, thank you very much for your listening through that long talk.
Well, we have as a memento some nice hydrothermally produced quartz for you to take home.
Thank you. Thank you, Bob. I like the copper. This is very Arizona.